day we have discussed about the carbohydrates and its classification. Okay, then in the classification we have found, first of all, what is the definition of carbohydrates? That initially we've defined carbohydrates are the compounds of carbon, hydrogen and oxygen, where the ratio of hydrogen and oxygen present in the compound are in the ratio of water. But later on we found that this definition is not perfectly correct, because some molecules with this formula are actually not carbohydrates. So we have changed it and we have incorporated a complete definition of carbohydrates, because carbohydrates are optically active. So we have mentioned that these are optically active polyhydroxyaldehydes and or ketones. Or those compounds which on hydrolysis, means if you react with water, those compounds which on hydrolysis give optically active polyhydroxyaldehydes and ketones. Okay. Then we have gone for the classification. In your textbook, 2 classifications are being given, but I have mentioned 3. So initially, the first classification what I mentioned is sugar and non-sugar. So the word sugar is very, very common to us, but somehow its definition is not known to us. So those carbohydrates which are crystalline, water soluble and sweet in taste are called sugars. All right. So we only know that the formula C12H22 and O11, which we use in our house, we call them as cane sugar or chemically sucrose, is only sugar. No. Varieties of compounds are there are sweet in taste. For example, glucose, fructose, lactose, maltose, and sucrose. These are called sugars. Plenty of sugars are there. And those carbohydrates which are amorphous, not soluble in water, and are flat in taste or tasteless, we call them as non-sugar carbohydrates. Second classification we have done on the chemical reaction, that we call it reducing sugar or reducing carbohydrates, non-reducing sugar or non-reducing carbohydrates. So what are the reducing carbohydrates? The carbohydrates which can reduce tolerance reagent or failing solution are called reducing carbohydrates or reducing sugars. But why do they do? So in the same definition I have written, they have free aldehydic or ketonic group in aqueous solution, or if you go by structure, we can say these carbohydrates contain hemiacetal group. That when we do the structure, then you will understand hemiacetal group present in them. And non-reducing carbohydrates are which do not reduce tolerance reagent and failing solution. That is, they do not provide any free aldehyde or ketonic group in the aqueous solution, or you can say the hemiacetal group within it is missing. They do not have any hemiacetal. All right. Then after that, we have gone for the modern classification of the carbohydrates in the form of saccharides. So saccharides can be classified into 3 categories. First one is called monosaccharides. Because these carbohydrates cannot be hydrolyzed. It is, if you react with water, they will not break down into simpler molecules. So these are called monosaccharides. So monosaccharides may have carbon ranging from 3 to 9. Then monosaccharides can again be classified into two categories. Those who are having aldehyde group, we call them as aldose, and those who are having ketonic group, we call them as ketose. So, depending upon the number of carbon, we can name them also. Suppose a monosaccharide contains 3 carbon atoms, we call them the aldotriose. 4 aldotetrose, 5 aldopentose. I told you an example of aldopentose, which we have even learned in lower classes. That is called ribose. Ribose is present in RNA, ribonucleic acid. Okay. Then if it contains 6 carbon, then we call them as aldohexose. So aldohexose example is glucose. Okay. Galactose. These are the example of aldohexose. And now if it contains 6 ketonic group, we call them as ketose. So similarly, 3 carbon, we call it ketotriose, then ketotetrose, then ketopentose, ketohexose, like that. All right. Then we go for second classification is the oligosaccharides. So these contain more than 1 unit of same or different monosaccharides ranging from 2 to 10. That is, if you hydrolyze them, it gives you 2 to 10 numbers of same or different monosaccharide units. Okay. Now, if it contains 2, then we call them as disaccharides. Disaccharides example, sucrose. If I hydrolyze sucrose, it will give you 1 unit of glucose or 1 unit of fructose. If you hydrolyze maltose, it will give you 2 units of glucose. If you hydrolyze lactose, lactose is the sugar which you get it in milk. It will give you 2 units of galactose and glucose. Then similarly, if it contains 3, then we call them as trisaccharides. Example of trisaccharide, I could give only one. That day also I told you that I'm not that well versed with the carbohydrate chemistry. Okay, so and moreover, I did not read it in a large extent. So in that case, I can give you only one example. Plenty of examples are there, but I know only one. It's called raffinose. So raffinose on hydrolysis, it gives you 1 unit of glucose, 1 unit of fructose, and 1 unit of galactose. Similarly, you can have tetrasaccharides. In tetrasaccharides, you will have 4 units. It may be same or generally it is different only. This is called tracheose. So if you for your NEET and all these things, if you wish to study, you can read in detail. Now, then after that we go for polysaccharides. Polysaccharides on hydrolysis gives large number of monosaccharides. But by definition, what should we say? That it should contain more than 10 units of monosaccharide units. Okay. So example is cellulose. Then we have starch, then you have glycogen, all about. All right. So after this classification, then that day we have discussed briefly then how to get the glucose. So glucose we do not prepare synthetically in the laboratory because it is largely abundant in the nature. So how do you get it? So there are 2 sources of glucose. One is the sucrose or cane sugar. So when you do the hydrolysis of cane sugar or sucrose with dilute hydrochloric acid or dilute sulfuric acid on heating, it gives us equimolar or same amount of the glucose and fructose. So, but I told you that this method is not being used. Simple reason is that it is difficult to separate the mixture. So the best method of obtaining the glucose is from the starch, because starch is made only of glucose. So, but starch is very complex and it is a complex polysaccharides. So it will not undergo this hydrolysis so easily. So what we do? we heat starch or we boil the starch solution with dilute sulfuric acid under pressure. Then it hydrolyzes to give us the glucose in large amount. So after that we cool it, create to crystallize, and we get it from there. Clear? So today we are going to discuss about the reactions of glucose and how to establish the structure of glucose. So we are going to discuss the structure of glucose, and in this process all the chemical reactions which will come across, we are going to do it. All right. Elucidation of structure of glucose. See, this is the way we try to find out the structure of any compound which we have made. First one is that, what is this molecular formula? Molecular formula, you know how to get it, that we have done in class 11. First, we will try to find out the number of carbon, hydrogen, and oxygen present in the molecule. Second, we will determine its molecular mass. So molecular mass, we can determine, we have already done the solution chapter. By using any colligative property, we can find out the molecular mass of glucose. The advantage of glucose is that it neither undergo association or dissociation. So you will never get a abnormal molecular mass. So we do the elemental analysis, that the amount of carbon, hydrogen, and oxygen present. Then we find the molecular mass, and from the molecular mass, with the knowledge that we have gathered, we determine its empirical formula, and from there we get molecular formula. Okay, the molecular formula of glucose we have already found is C6H12O6. Now we have to find in which position this carbon, hydrogen, and oxygen are present. We have to find out, and we'll count it. All right. So first duty is that the 6 carbon which are there, is it linearly linked like this, or is there any branch? It may happen. See, either it is like this, or it is like this, or some branchings are there. So we have to find it. So what we'll do? We'll carry out the reduction reaction. So now we'll do, we'll start chemical reaction. Chemical. So first we'll carry out reduction. The glucose is difficult to reduce. So we'll carry out the reduction with one of the very strong reducing agent like hydrogen iodide. Reduction, or we can write reaction. Reduction or reaction with hydrogen iodide. So what we would have done? Aqueous solution of glucose is boiled for a long time. With hydrogen iodide. Okay. Then what happens now here? We found that when we have boiled this glucose with hydrogen iodide for a long time, okay, in that case, very interestingly, we get hexane. We can call it normal hexane. Normal hexane means what? It is a linear chain. There is no substitution. Normal chain. So the hydrogen iodide has removed all the oxygen, irrespective the oxygen is in the form of hydroxyl group or in the form of carbonyl group. So it has given us the first information that all the 6 carbon are linearly joined. That is, they do not have any branches. All right, they do not have any branches. So here I'm going to write X6 with excess hydrogen iodide. So we have finished the problem with carbon. Now we have to find out the nature of the hydrogen and oxygen present. See now, oxygen is present always in the form of functional group. So what are the functional group oxygen can have? Oxygen can be present in alcoholic group, OH group. It can be present in the form of ether. It can be present in the form of aldehyde, ketone, carboxylic acids. Okay. Now we can rule out the presence of oxygen in the form of ether. Why? Ether functional group always occur in between the carbon chain. We do not have. If you would have ether, because we have already studied, then the hydrogen iodide would have broken this molecule into smaller fragments. So it is not possible. Ether is not. All right. So what we have done, we will now do the reaction to find out whether it has carbonyl group or not. Okay. So we'll write now here. Reaction with hydrogen cyanide and hydroxylamine. Hydrogen cyanide and hydroxylamine. We know hydrogen cyanide undergoes addition reaction with aldehydes and ketones, and hydroxylamine undergoes addition elimination reaction with aldehydes and ketones and to form oximes. All right. So we have taken 2 different reagents showing 2 different types of reactions. So reaction with hydrogen cyanide. Okay. Now, dear, I have to write this formula, but initially when the people have done it, they did not know the structure. But otherwise, if you do not know the formula, I cannot write the product. So please excuse me. And in the same way, it is written in your book. Okay. Now I'll write it like this. So we know that hydrogen cyanide reacts with aldehydes and ketone to give us corresponding cyanohydrate. See now, what is going to happen? You will get cyanide, then C, OH, H, CH, 3, H2, OH. Sorry, it is 4. Okay. So here you have written glucose and you get the cyanohydrate of glucose. Okay. So you got here glucose. And this is the you get here now glucose, cyanohydrate. Please write. সবই ঝাড়ু দেওয়া হচ্ছে, সব কিছু হয়েছে। আর ফুল তোলাটাই ভাঙার পরে কুড়িয়ে এই যে আমার শরীরে মন কুড়িয়ে নিচ্ছে এটার কথা হয়ে লাভ নাই
আমি নাম্বারে কেন ডাকি অনলি বিকজ অফ জোসেফ জোসেফ আমাকে ফোন করে নিজে বলেছে না নামে ডাক্তার না
okay then you get here this is called glucose oxide see any portion on the board if you can't see you please tell me from here I don't understand huh? So now these two reactions has proved that glucose has a carbonyl group because only carbonyl group can react with hydrogen cyanide and hydroxyl. So because of that two reactions are done. One reaction may not give us the correct information. Now we want to know whether it is aldehyde or ketone because we know hydrogen cyanide and the hydrogen cyanide and the hydroxylamine reacts with both aldehydes and ketone. Now we have to verify whether it is aldehyde or ketone. So generally what we do, because in aldehyde ketone chapter I told you that how can you distinguish the aldehydes and ketones? We distinguish it by reaction with Tollens reagent and Fehling solution. Aldehydes undergo oxidation with Tollens reagent and Fehling solutions to give us carboxylic acid, and ketones do not undergo. So when we tried here, we find very strange that in case of the monosaccharides or glucose, because we know monosaccharides can be classified into two categories with aldehydes and ketones. Both the aldehydes and ketones they react with the Tollens reagent and Fehling solution, and it is very interesting that it is not being given in your book. So we should know for little more, and not only that, it is going to help us in our entrance exam. So this portion I'll write it for you, but please, you don't have to read for your school. We'll write now here. Both aldose, aldosal, aldoses, and ketoses get oxidized by Collins reagent and Fellings solution to corresponding carboxylic acids. Why? It is because ketoses rearrange in alkaline medium to aldoses and vice versa. Please write. Then I'll show.
Poly office course দিয়ে চালকনের মতন করে রাখতে হবে হ্যাঁ ঠিক করে বুঝিয়ে
First time I was preparing the ঘটনা
দিয়ে তো তরকারি করবো কোর্স দিয়ে চালকনের মতন যাচ্ছে
Okay, now see here what happens. Try to understand. Very interesting. So I write down now fructose. This is the formula, structure of fructose. Fructose is a ketohexose. It is a ketonic. Okay. Here I write CHOH 3. CH2OH. Okay, this is fructose. What is this? This is a ketohexose. Okay. It is in alkaline medium. Why do you call it alkaline medium? Because in tolerance reagent, what do you call it? Ammonium silver nitrate. Means we add their ammonium hydroxide, so it is alkaline. What is filling solution? Filling solution is we prepare by copper sulfate and alkaline solution of sodium potassium tartrate. So there also you have alkali. That is, it is in alkaline medium. See what happens. See. It will undergo tautomation. So what we are going to get? I told you this is not in your syllabus, but you are not too small to understand. it undergoes tautomerism. Then see what happens. Then, in that case, this hydrogen from oxygen migrates here. How it will come? See, the electron has come, H plus will come here. So what you will get now here? See, very interesting. You get aldehyde. I'll write now here 4, 3 plus 1, 4. Okay, I will not write like this because you read it after many days, you will forget. That you may think that sir by mistake or you by mistake you have written it. Okay. See how this fructose has been converted into glucose. Okay, so you get here now aldohexose. So it is not only case of the glucose and fructose. Even if you take aldotriose, aldotetrose, aldohexose, all of them they show this type of rearrangement. Okay. So now, according to the knowledge that you have gathered from aldehyde ketone chapter, we know aldehydes undergoes oxidation to carboxylic acid by Tollens reagent and Pelling solution. Ketones do not. But look at this peculiar thing of this carbohydrates. See, here ketose become aldose, and aldose can become again ketose because of the I have given a reversible sign. Okay. Now I'm writing the name of this rearrangement. This rearrangement is known as this rearrangement is known as de Bruijn-Kenstein rearrangement. This is the name of only one person, huh? So this is important for your entrance. So this experiment cannot be done to distinguish the carbonyl group.
Sir, done.
So now what our conclusion? Conclusion is that hence both Tollens reagent and Fehling solution cannot distinguish aldoses and ketoses. This I am writing only for your entrance. Okay. No, I will not write like this. I will do little change it here. I will not write here both. Because for entrance, Tollens reagent, comma, Benedict solution. Benedict, because I have given you 4 options. Tollens reagent, Benedict solution, 5 options I have given. Tollens reagent, then Fehling solution, then Benedict solution, then Schiff's reagent, and see, Tollens reagent, Fehling solution, Benedict solution, Schiff's reagent. With 4 generally we use distinguish aldehydes and ketones along with bromine water. Okay. So this one we have given because if you use any 3 of them, both aldoses and ketoses or glucose or fructose, they react. Now here you will write down the Schiff's reagent does not react with glucose. Schiff's reagent does not react. So this is also being ruled out. It is we have to use an oxidizing agent, mild oxidizing agent, which is not being used in alkaline media. We have to do this in acidic media. Okay, this is the way a chemist approach in the laboratory. He observes everything, reaction condition, medium, everything they mention. After that, he keeps on trying the other alternative. When we okay. So now I told you this is not for your school. So now the dissection that I'm going to do is in your syllabus. Okay. So reaction with bromine water. Bromine water. We know that halogens are having highest electronegativity along their respective period. And their electronegativity decreases down the group. As I told you that aldehydes can be easily oxidized. So we need not use strong oxidizing agent. We are going to use weaker oxidizing agent. So in that case, we do not take fluorine. And moreover, fluorine is hazardous. We do not take chlorine. Why? Because chlorine is gaseous. We take bromine. Bromine is liquid. It is easy for us to handle, though it is extremely corrosive to our skin and if you for our eyes. Bromine water. Now see, how does the bromine oxidizes? So right now, H2O, Br. So this is called bromine water. This is solution of bromine in water. Bromine is not highly soluble in water because water is a polar solvent and bromine is a non-polar compound. But it goes to water to a certain extent. How does it? What will be the appearance of this one? Brown in color. Now, what will happen? Bromine is going to displace oxygen from water. So you get here now HBr and you get here nascent oxygen. This is the oxygen which oxidizes aldehydes. So right now here, this equation is not being given in your book. They have written directly the product. I do not know why they are doing all this. And here I will write here H2O plus Br. This is not been given in your book. What happens here? This will be aldehydes immediately get oxidized to carboxyl. So you get this. See, this oxygen has oxidized this one. And this compound is called gluconic acid. It's called gluconic acid.
ABC শুরু হয়ে গেছে।
So for examination purpose, this reaction is very important. So now we have proved that in glucose we have one aldehyde. So formula of glucose is C6H12O6. See, out of 6 oxygen, we have only got information about one. That one of the oxygen of 6 has formed or present in the form of aldehyde. Now we have to find out the status of 5 more oxygen. So in that case, what we will do now? We are going to do a reaction with acetic anhydride. Why we know that acetic anhydride, when we react with alcohol, it gives us a star. Reaction with acetic anhydride. Glucose, when heated with acetic anhydride. How does it look like? Because you don't read now, there is a problem. This is acetic anhydride. Okay, to form glucose penta acetate. This proves that glucose has 5 weights. This what weight? Alcoholic groups. Okay. So if I have written this one, CH, okay, I write it like this. Here you have four weights group, and I react it with then you will get here you get this. It is called glucose penta acetate. This is the acetate group. This one you don't write. See here. How does it react? I have taught you chemistry in detail. You can't say that you do not know. If you did not understand, you will never ask me. So see here. What happened? It goes out. This H goes here. Then what you get now here? R O CH3 plus CH3 CO4. See, this is the reaction. So it proves that alcohol reacts with acetic anhydride to form ester. So this is the acetate ester. So this is the one that you have got it here. Don't write this. Okay. Okay, now see. So we have found that In C6H6, 6 carbons are joined in a straight line. We call it linear. Then out of this 6 oxygen, 1 oxygen is aldehyde and 5 oxygen are alcohol. Now we should know, these alcohol, are they primary or secondary or tertiary? Tertiary is not possible because it is a straight chain compound. So we have to prove that it is primary or secondary. All right. So now we'll do oxidation with nitric acid. I forgot this number. You can see maybe 6 or 7. Is it 6 or 7? Hello.
So 6.
6. So now we'll write here. Reaction with nitric acid. Glucose on reaction with hot concentrated nitric acid get oxidized to saccharide acid. See, when we have taken mild oxidizing agent oxidizes aldehyde to carboxyl. Okay, but mild oxidizing agent cannot reduce a primary alcohol. And second thing we know, a primary alcohol on oxidation gives us carboxylic acid, and secondary alcohol gives us a ketone. All right. So when we have done the oxidation with concentrated nitric acid, this also get oxidized, this also get oxidized. All right. So now it proves that the last carbon is a primary alcohol, and these are all secondary alcohol. Okay, it's called saccharide acid. Saccharide acid. Now we want to prove whether the compound that you got does it undergo any rearrangement or simple oxidation of glucose. See, this is being proved because when we have carried out the oxidation of glucose with mild oxidizing agent, like the bromine water, nothing has happened to the molecule. So I'll write now here Br2H2. So we got this. That you have already done. Okay. So glucose, and we mentioned it as a gluconic acid. Now this we already had because we made it. Now this is being oxidized by HNO3. See, we found this compound. If you oxidize it, you get the same saccharide acid. That is, we can find that we did not break the molecule. Okay, this is the one. Clear? So this is being double verification. Because to establish a structure, you have to be very, very careful. Otherwise, if you get wrong structure, then later on, people will, if they accept wrong structure, and after that, some of the scientists may find it, no, your structure is wrong, then it is a matter of prestige. So all the reactions which is being given in your textbook, this is only to establish the structure of glucose. Only to establish structure of glucose. Glucose shows many other reactions, but these are not being included. Anyway, you have learned that whenever you make a compound or get a compound from nature, how do you actually find its structure? Because molecular formula does not give us any information on the structure of the molecule. All right, so this is the way we do it.
Sir,
Yes.
that second line, glucose on reaction with
Bromine water.
with what, sir?
Bromine water.
No, sir. The first line.
This one.
No, sir. See, no, that point number 6. Second line. Second line.
Yeah.
No, sir. Yes, sir. Glucose on reaction with
Glucose on reaction with hot concentrated nitric acid. Get
what, sir?
oxidized to glucose on reaction with hot concentrated nitric acid, NiTRIC, nitric acid, get oxidized to saccharic acid.
Thank you, sir.
We got an information that what will be the structure of glucose. Okay, now, no, I should not say structure of glucose, it is the structure of this aldohexose. Then after that, we have to find out. See, this is the ultimate. So many carbons are there. Which way I should put which group, right or left? Okay, see, very interesting. So here you have to go for now assumption, or you have to remember it. I will not say you have to by heart it. By hearting and remembering are two different things. When you by heart, you do not use logic. See, very interesting. This carbon, this carbon, this carbon, this carbon, these are all asymmetric carbon. That you see here, this valency of this carbon is not being satisfied by this same group, same atom or group. See here, it is H, aldehyde, OH, and entire group. Similarly, see here, H, OH, this is entire group, and this entire group. So it has 4 asymmetric carbon atoms. Please don't write, I'm telling you. This is aldohexose. Aldohexose, don't write. Aldohexose has 4 asymmetric or chiral carbon atoms, and thus can have, see, I'm leaving a gap here. We can calculate number of optical atoms. Okay. How do you calculate number of optical isomers? I taught you when you in hello alkene, but you forgot. See, is equal to 2 to the power n. What is n? N is the number of asymmetric or chiral carbon atoms. How many we have? 1, 2, 3, 4. So how many will get? 16. Okay. We can write 16 structures with that. And interestingly, we have isolated all of them. All of them are stable. Out of the 16 structures, this structure is called glucose. So, this is the structure of glucose. It has taken a lot of time to people to find out that structure. And you know, in optical isomers, whatever the structure, it will have a mirror image. We call them enantiomer. So, I will get a reflection of this one. That will also be called glucose. So, when you have 16 optical isomers, it is actually there are 8 structures are there. 8 structures, and with their reflection, 8 into 2 is 16. So, if I write one of them is glucose, which rotates the light towards right, other will rotate the light towards left. Okay. So, one will be dextroglucose, other will be riboglucose. So, this structure is the glucose that we are going to now discuss. This is the substance which gives us energy. It is mirror image. If you take in kg also, that will not give you the energy. All right. So, this is the structure of glucose. Yeah. 16 number of optical isomers. Then why do you tell? Why do you keep quiet? This way the process becomes very slow, nah? Otherwise, I simply write and then I erase it. Okay. Now we have to discuss some geometry of the glucose. Okay. So we'll call to be relative configuration of glucose. Okay. Right here now. Glucose turns plain polarized or monochromatic light towards right. And is dextro rotated. Okay. So what should I call it? And so it is also known as dextrose. It is, I'll again write down the structure. What is the new name we can give? So we'll call this to be plus glucose or dextrose. I told you there are so many confusions are there that which side which group is there. So to find out the actual structure, it is little difficult. It's a thing which you cannot do by ourselves. Sometimes we take the help of others. Okay. So in that case, to find out the structure, when nothing happens, then we, of our own, we say, no, it is like this. See, whenever in your house, you are having 2-3 brother and sister. Now, brother and sister can be distinguished, but sisters may not be distinguished. So in that case, how do we distinguish them? We put different name for these persons. And when the names are being given, is there any logic? Parents sit down and decide a name. And this name is being arbitrarily given. So please remember, on 2-3 things we do not have any control. One, our birth. Our birth is not being decided by us. Second, your religion. If you are born in a Christian family, our tradition is that the child will be baptized to Christianity. If he born in a Muslim family, then he becomes a Muslim. And if he born in a Hindu family, it will be like this. All right. So we cannot decide our birth, we cannot decide our religion, and we cannot decide our name. Okay. See, when you grow up, if you are born in a Khasi family, if when you grow up, then in that case, you can learn different language. But can you change your name? Name cannot be changed. So these are arbitrary decisions. So when we actually could not decide the actual structure, what name should be given. In that case, we take the help of a reference. Okay. So to decide the configuration of carbohydrates, their structures are compared with glyceraldehyde molecule. This is a reference. All right. How does the glyceraldehyde molecule look like? CHO, CH, H, and CH2. See there, this is aldotriose. Okay, it is optically active. Why? Because this carbon is asymmetric. 2-hydroxy, so it is polyhydroxy, and it is an aldehyde. Okay, and what is this mirror image? It will be just opposite. So it has two isomers. All right. So name of this one, when it rotates the light towards right, it rotates the right towards left. So right now here, plus glyceraldehyde, and this is minus glyceraldehyde. See, plus and minus, unless you do not determine experimentally, you do not know. But then the name should be given. You can see they are just like twins, almost look alike. A stranger cannot distinguish that whether they are twins or not, because if they have seen this person at different place, they will feel that it is the same person. Okay, so before that, what we do? We put one capital letter D. This D has nothing to do with the rotation of light. D is the structure, and this is called L. L-glyceraldehyde. Okay, so this is called relative configuration. We have given a specific name to identify their structure. Okay, so D-glyceraldehyde and L-glyceraldehyde. If there is a, see, generally we find in twins, the parents always put the same type of dresses. But if it is a question of individual exceptions are there, they are going to a suppose prize distribution ceremony, then there may be fake also. One person may go and take the other's prize. In that case, if they wear this separate color of cloth, In that case, one can distinguish that one with the pink, other with the blue. So this is being given for distinction. D-glyceraldehyde and L-glyceraldehyde. Now, how to compare this with this? See, it says, if any compound, not only carbohydrate, any optically active compound, if you can prepare from this, we will call it D. And if you can prepare from this, we will call it L. See, this glucose, see, compare. Last two carbon, it is not the same. Yes, that is, we can prepare this compound from this. So because of that, we put one D before the name. So this is called D plus glucose. Okay? So what I can write now here? If any compound can be obtained from D plus glyceraldehyde, then it is assigned D configuration and is similar for L minus. That is, it's this compound optical image will be L minus glucose. Can I wrap this portion?
Yes, sir.
Hello? Okay. So I can write here now. This I'm not going to change because this is not asymmetric. So if I take this mirror image, we just see this mirror image. Is it not? So we'll call this to be L minus glucose. So our body wants this, not this. This cannot produce energy for our body. This is the one which is going to produce energy for our body. Okay. So enough for today. So we'll discuss biomolecules because most of you want to